All right, this question reads, state Newton's second law of motion. Arguably the most important law that students that are first learning physics will come across, maybe even the most important law ever. The sum of the forces equals mass times acceleration. Okay, so that's one way to sort of think about Newton's second law, but that's a special case, right? This is a special case of the more general definition of force, which is that force is the rate of change of momentum. Okay, and that's really a good way to define force. And because of the way momentum is defined, right, as mass times velocity, that if we're changing momentum, it's like the mass times the final velocity minus the mass times the initial velocity. That would be the change in momentum. And if the mass is constant, like it was in the example question 1 of this paper, we could factor that out and we just have mass times v minus u over t, which is acceleration. And so this is the same thing as this. So we could, state Newton's second law, like for a body with constant mass, the acceleration is directly proportional to the net force and in the same direction, right? So that's a nice way to think about it when, a lot of the times the mass does stay constant. It's really just saying if mass is constant and acceleration is going to go as the force, right? They're directly proportional. So if you push something with a given mass with more force, it accelerates more. It's inversely proportional to the mass, right? So if you push something that's very, very massive, right, it's not going to accelerate so much compared to if you gave the same force to something with little mass, right? So the mass and the force, sort of for a larger mass, it would require a greater force to achieve the same acceleration. All right. So let's say for a body of constant mass or an object, the acceleration experienced is proportional to the net force. And in the same direction. All right. So something like that might be good for Newton's second law of motion. We'll remember to actually check the mark scheme this time before we end the video. But if you would have checked that last one, you find that everything checked out okay. All right. Let's see how we're going to put this to good use now. It says the constant resultant force F acts on an object A. The variation with time t of the velocity v for the motion of A is shown in figure 2.1. Let's examine that figure more carefully. It looks like it's going from 4 something to about just under 9 in a time of 4 seconds. Okay. If we're just looking at a velocity time graph, we could think, we can anticipate some calculation. If we took the slope of this line, we were able to calculate that, then we would be able to deduce the acceleration. The rise in meters per second, the run in seconds, and the rise over run with meters per second, or meters per second squared are the units of acceleration. If we took the area underneath that curve, that would be an area problem, obviously. So we'd have meters per second times seconds, and the seconds would cancel, and we'd be left with meters of displacement. So in general, the area underneath a curve on a velocity time graph is the displacement, and the slope or the gradient is the acceleration. So the derivative of velocity with respect to time is acceleration. The integral, if we integrate this, right, we get the displacement. The mass of A is 840 grams. Calculate for the time from t equals 0 to t equals 4 seconds, the change in momentum of A. Change in momentum. Change in momentum equals the final momentum minus the initial momentum. The final momentum is going to be the mass times the final velocity minus the mass the initial velocity. The mass is 0.84 kilograms. So see, right away, you know, some students might make a mistake by just substituting that in for mass. Got to remember the base units, right? So there's 840 grams is 0.84 kilograms. There's 1,000 grams in a kilo. So we got to divide this by 1,000 or just kind of move the decimal point over 3 places if you're comfortable with that. Here we need to just take care to sort of read off the graph that's quickly going out of view and not cooperating very well with us. Just let your eyes steady there. There they go. All right. And let's take care to be mindful of the scale. If this is 4 and this is 5, it's like 10 lines between there and there. So each one is 0.1, 4.1, 4.2 is the initial velocity at 0 seconds. And then this one is 8. So that line right there is 8. So 8.1, 2, 3, 4, 5, 6, 7, 8. 0.8, I could have just counted down from 9, right? 8.9, 8.8. So that's V. So the final momentum is, you know, the final velocity times the mass. The mass didn't change, right? It's a constant 0.84 kilos. So 0.84 times 8.8 meters per second will give us units of kilogram meters per second. We'll subtract away the initial momentum, which was 0.84 kilograms times 4.2 meters per second. And here again, we just factor out the, you know, the constant mass, and we have V minus U. We know that it occurred over 4 seconds, and so we could calculate, you know, the time. And it looks like we're going to sort of have a chance to do all that because they want us to calculate the force. So just take care, you know, you're answering the question that is asked. 0.84 times 8.8 means this thing had a final momentum of 7.392. Its initial momentum, 0.84 times 4.2 would have been 3.528. 7.392 minus 3.528 is 3.864. I would round to 3.9. I'd make sure that my answer was right on that line, just like you see right there. 3.9 kilogram meters per second is the change in momentum. Now, force is the rate of change of momentum. So since we already know the change in momentum, the simplest path forward now to calculate the force is to just recognize that delta P over delta T is force. And we know delta P is 3.9, happened over 4 seconds. Now let's sort of explore how equivalent to that, you know, sort of we could look at, just like I showed at the definition of state Newton's second law of motion, we have this delta P that we've already kind of worked out, 0.84, and now I'm going to factor it out. So 0.84 kilograms times the quantity, 8.8 minus 4.2 meters per second. So it's the same working we did down here. I just factored out the common mass. If I then divide this by delta T, there's my 4 seconds of time. Remember, it went from 0 seconds when it was going 4.2 meters per second. 4 seconds later, it was going 8.8. So that's the change in velocity over time. The rate of change of velocity is acceleration. So this calculation right here is the acceleration. That's the mass. So how are we getting the force? Mass times acceleration, right? Or the change in momentum divided by time. So if we've already sort of done the change in momentum, we already know the numerator, 3.9, we just got to divide it by 4 now. Note that we didn't have to sort of calculate the acceleration along the way. We could have done that. So if I've got this 3.864 in my calculator, I'm just going to divide that by 4. And I get 0.966. So I ultimately solve for the force as 0.966 newtons. Okay, what was the acceleration of that thing? 8.8 minus 4.2 means it changed its velocity 4.6 meters per second divided by 4 seconds. So its acceleration was 1.15 meters per second squared. If you multiply that by 0.84 kilograms, we should get the same answer, and indeed we do, 0.966. So whether you factor out the common, term, the mass, calculate the acceleration, and then multiply that by mass to get the force, or you think about it the way that we define force. If you had a question that said, how is force defined? The rate of change of momentum. That's the better way to think about it, because this is a special case when mass is constant. That's how we can factor it out. Mass won't always be constant. But any way that we look at it, we can get 0.966. I'd round that to 0.97. So I feel pretty good about reporting the net force here. I'm sorry, the force here, 0.97. So let's clear this up. And let's say this is 0.97. Remember, this was 3.9. So it's about 3.9 divided by 4 would give you 0.975. You might round it to 0.98 if you just sort of remember it was a little bit less than this. So if you use this number, you might calculate 0.98. Let's see what the mark scheme says about it. Question goes on to read, the force F is removed at t equals 4 seconds. And so, all right, object A continues at constant velocity before colliding with an object B as illustrated. So collided, right? This kind of a setup here. We kind of know that we're going to have some conservation of momentum probably to help us out. One of the great conservation laws of physics. The force F is removed, continues along, colliding with B as illustrated. Let's remind ourselves of sort of what exactly we've got here. We know that this thing is now moving at 8.8 meters per second. Like that's when the force was removed. So we had this constant force that was giving it constant acceleration, speeding up until it got to this final speed of 8.8. So we have this mass going this fast. We know what sort of the momentum of this thing is, right? It was sort of, when we calculated the change in momentum, it was this minus its initial. That's what gave us sort of the force that allowed it to accelerate up to this speed. Here, this thing's at rest, and so it has no initial momentum, okay? If object B is initially at rest, they give its mass, the objects join together and have a velocity of 4.7. So this is like our ballistic pendulum, right? This is our dart, it's got some Velcro right there. This is our target, it's got some Velcro right there. It's gonna collide, stick together, right? And have a shared velocity of 4.7. By calculation, this shows how much of a nerd I am. When I read that introductory prepositional phrase, by calculation, I do get a little bit excited. Like my favorite verb, one of my favorite verbs, you guys. Calculate. When you're calculating something, it's kind of like, hey, you can't argue that, according to my calculations, this is what it is. And the calculations could be wrong, but if it's, well-founded in physics, that's a pretty solid answer right there. So forgive me, but I'm getting a little bit excited right now. By calculation, here we go. Show that the changes in momentum of A and B during the collision are equal and opposite. Show that the changes in momentum of A and B during the collision are equal and opposite. So let's just be very formal about this. We know by calculation, good, we're going to do some calculations, changes in momentum. So this thing is going to have a change in momentum, and this thing is going to have a change in momentum, and they should be equal and opposite. Okay, let's start with object A. The change in momentum of A equals the final momentum of A. Well, we know that it's going to be sort of going, it's a mass now of 840. See, that's what's tricky about this, is that you've got this combined object. So the change in momentum of A and B. So I guess, is the final momentum of the combined object AB its final momentum? I guess you have to sort of consider it that way. So we've got 730 grams plus 840 grams is 1,570 grams or 1.57 kilograms. 1.57 kilograms. Did I do that right? Yeah, all right, 1570. So I think the final momentum is going to be 1.57 kilos times 4.7 meters per second, because that's the final sort of momentum of the new object A plus B. But the initial momentum of A was 0.84 kilograms minus or times 8.8 meters per second. So what does that give us? 1.57 times 4.7 means that the momentum of this sort of new object was 7.379, and 8.8 times 0.84, that was our 7.392 value. 7.379 minus 7.392 is negative 0.013 kilogram meters per second. I'm not so sure about this. If we think about B now, the changes in momentum of A and B during the collision. So the change in momentum of B would have been this same value, like it's this object also, it's 1.57 kilograms times 4.7, so it has that 7.379, but its initial momentum was 0, right? So right away, we know that this is not a good approach to the calculation. Nope, that's no good. The initial momentum would have been 0 for this thing. So I think maybe we need to approach it a little bit differently here. Let's junk all that, forget all that, you guys, my bad. The changes in momentum of A and B during the collision. Okay. So we kind of have this, the initial momentum equals the final momentum, okay? The next step to this is explain how the answers obtained in one support Newton's third law. Well, the force is the same force that's sort of acting on both of them. A little bit frustrating. It's the same force that's acting on both of them for the same amount of time, and so the change in momentum, should be the same. That's just restating Newton's third law. All right, where are we at? There we go. Let's think about it the way that we did with the ballistic pendulum. So we have something that is 0.84 kilograms times 8.8 meters per second plus 0.73 kilograms times 0. So there's no initial momentum from that, and that's going to equal the final momentum. There's our 1.57, right? The combined mass going at 4.7. So 1.57 times 4.7 equals 7.379 kilogram meters per second. All right, that is the final momentum. The initial momentum came from this. So we had 8.8 times 0.84, 7.392 plus 0. Okay. So 7.3, we can see that all the momentum is conserved. Like these numbers are sort of close enough together. They kind of rounded this to 4.7, right? So 7.4 basically, 7.4 equals 7.4. So momentum is conserved here. Show that the changes in momentum of A and B during the collision are equal and opposite. Let's take, this kind of shows that the momentum is conserved there. So the change in momentum, I'm not exactly sure about this. Show that the changes in momentum. And certainly the way that we initially approached it was incorrect there. So we'll have a look at the mark scheme here and take a look and make better sense of that. This one says by reference, explain how the answer is obtained in one support Newton's third law, right? So we have forces exist in pairs, equal in magnitude, opposite in direction. And so the force that A exerts on B is equal and opposite to the force that B exerts on A, such that the total momentum is conserved. By reference to the speeds of A and B, explain whether the collision is elastic. So now you might recall elastic versus inelastic collisions by reference to the speeds of A and B. So the relative speed of approach equals the relative speed of separation. So these things sort of see each other. You know, B sees A coming in at a speed of 8.8, and then the relative sort of speed of separation is 0 because they're moving together, right? They sort of join together. So there is no relative speed of separation, and therefore we can conclude that this is an inelastic collision, right? Even the words join together kind of contradict the very idea of elasticity, elastic, right? Not bouncy if they're joining together. So we can say that this collision is inelastic, right? Because the relative speed of approach does not equal the relative speed of separation. Remember that when it does, that means that the kinetic energy has been conserved. There's been no loss of kinetic energy. So the relative speed of approach does not equal the relative speed of separation. So always answer the question. So the collision is not elastic. All right, let's have a look at the mark scheme and really see what they said here about this by calculation. I'm so excited about that question. All right, so number 1 for part D. Question 2. All right, paper 23, May, June. So looking at the CIUnotes.com website, great resource. We were just looking at question paper 23 from the summer of 17. So we're going to queue up the mark scheme for the same year, same paper. Let's look at question 2 now. And we've got the resultant force is proportional or equal to the rate of change of momentum. So remember, we sort of talked about the rate of change of momentum for a body of constant mass. The force is proportional to the acceleration. Okay, would they give that mark there? Again, it's sort of the better way to think about it. 3.9 we got for that. 0.97 we got for that. Again, just sort of dividing the change in momentum by the time. Change in momentum for A. So let's see how they did this one here. So they took the mass times the change in its speed. They got negative 3.4. And the change in momentum for B, they took its mass times. So they just kept the mass separate. They didn't worry about, it's just like, okay, well, this object, this 0.84 kilogram object is now going 4.7. Yeah, it's attached to this one going 4.7. So yeah, we were on sort of the right track, I think, the way I set up the first time. I just got confused with the whole idea of the inelastic collision. So there you go. The change in momentum for B is equal and opposite to A. So this here, we've got final minus initial. So you see how you get a negative vector for A. That's the other thing to sort of take care of. You get a negative. So the change in momentum for B is equal and opposite to A. Yeah, I would take those marks away. I mean, I kind of showed that momentum is conserved there. So, no contribution from the initial one. But look, if you separate them out, you can show that. So the change in momentum equal for A and B. The force is the change in momentum. The time and the time of the collision is the same. Hence, the force on A and B are equal and opposite as for Newton's third law. Right? We talked about that. And we said that it was inelastic for the reason that the relative speed of approach is not equal to the relative speed of separation. So that one sounds pretty good there. So yeah, the question was kind of clear where it said, the change in momentum of each one. And so not combining them into sort of the new mass, but leaving each one separate and just dealing with the velocities like that, you can show that they're, sort of the same to within out to the hundredths place anyway. All right, so there's that one.